Schwarz-Grün, dass ich das reingesteckt habe. Und das muss wahrscheinlich noch auf
Okay, let's start. So hi everybody, welcome to Microfluidics 1. Today is all about diffusion and heat transfer. So I hope some of you have already watched the videos and got a little impression on the principles, on the fundamentals of heat and diffusion. And just to remind you a little of what you watched, I want to start with some magnitudes for thermal conductivity and also for heat for the heat transfer coefficient. And so what you can see in general is a trend that from solids over liquids to gases, that the thermal conductivity gets lower. Do you have any idea why that's the case? If you think about the micro modeling that we introduced at the start of the lecture. Yeah. Right. Right, that's exactly it. So if you think about the micro modeling, you will remember that in a solid you have somehow a grid and the molecules are very close together. For the liquid, they are still dense, and for the gas, they are all around the room basically, and that's why there's a bigger distance. And to transfer the heat, they have to bounce against each other, and this basically is what you can see on the in the table here. So you can see that for the gases, the heat conductivity is not as big as it is for some solids. Does anybody have an idea why metal in particular is well for the heat transfer? Yeah.
It also transports to electrons.
Right, that's it. And if you now think about the parameters like pressure or temperature, it's obvious that there is somehow an influence. So if you look at the air, think about the model again. You have particles all around. If you now start to compress them into a smaller room, they are closer to each other. And this automatically leads to a better heat transfer. And that's what you can see right here in the parameters comparing the air for, well, air at 1 atmospheric pressure and 50 atmospheric pressure. Okay, so if we now move on to the heat transfer coefficients that are known. So if you remember the video, the first thing that I introduced was the conduction, and then there's the heat convection. And I mean, most of you probably know convection already from your laptops or your computers. So they usually people use fans to cool elements of your devices. And it's a very efficient way to cool or to heat up. And on the right-hand side, you can see once again a table presenting different coefficients for different types of combination. And just keep in mind that there's free convection and forced convection. And the free convection is always a natural flow, which is in general based on density differences. And the forced convection is really a flow that is forced onto your surface and cools or heats up the surface. And what you can see right here is that for liquids, in this case water, the coefficient is higher than for gases. And yeah, any idea why that's the case? So basically, if you, I mentioned in the lecture, if you look closer at the surface, so if there's a heat transfer, it looked a little like this. So if that's the temperature. And I mentioned that very close to the surface, the velocity gets lower and lower. This basically means that close to the surface, there is the flow is not dominating, but the conduction from the solid phase to the liquid phase is dominating. So the liquid isn't moving at all at the wall, and it slowly starts to accelerate the further you go away from the wall. And this means in this area close to the wall, you have conduction. And then again, you can think what we just discussed, that in conduction, density is important of the particles, how close they are together, and so on. Is it clear? And just as comparison, we are not going to detail this further in this lecture. I also added the values for condensation. So this is basically only that you get an impression how effective condensation can be. So how effective our body basically is if it's hot and we're sweating and cooling down by this condensation effect. Okay, so for today, I prepared an example which is, well, quite popular at the moment because of the energy issues that we have all around. And I want to calculate with you on a simplified model, obviously, how you can calculate the heat loss through a wall of a house. So on the right-hand side, there's a picture of a heat cam that measures the radiation of a building. And you can see that there are some hot and some cool areas where the insulation is better or worse. And just to come back to our real topic, this can also be done, obviously, on a microfluidic scale. So you can also have a look at microfluidic chips and see how the temperature is evolving. If you remember the introduction lecture, we were talking about PCRs and how to heat up liquids. This is really, so it's a very crucial point in microfluidics. And to start with, I prepared a little picture on the right-hand side. So what you can see is a wall, and there's an inner side here on the left-hand side, and there's an outer side on the right-hand side. And what we want to calculate now is the heat flow from the left, so from the inner to the outer side. And to do so, we need to introduce parameters, which we require to describe our problem. And we also have to do some assumptions so that we are able to get equations that we are able to solve. And I want you guys now to think a bit about possible assumptions. It's not always easy, especially if you're not familiar with the topic, but I guess that you will come up with one or two, which we will use for this exercise for the calculation. So please take a minute, think about it, and then we will collect your ideas and continue with the exercise. Okay, so does anybody have an idea about an assumption that we could take? Yeah, maybe you. Do you have an idea? Yeah. So yeah. Right. So the thickness of the wall is a parameter. Hmm.
The coefficient of the wall, of course.
Yeah.
The conduction coefficient.
Right.
Yeah.
Mhm. Yeah.
Makes a difference if there's a gas.
Right.
Just if you imagine that solid state, molecules are in solid state inside, there would be
Yeah. Yeah. There were a lot of good points. So especially regarding the parameters, you also had an idea.
Yeah, we assume that the gradient is only
Right. Yeah. That's also a very good assumption for this case. Otherwise, it gets quite complicated. Okay, then let's have a look at it. So we will also assume that we have steady state because we don't really want to consider temporal changes because then we wouldn't be able to solve it analytically. We also assume that that the walls at the outside, so the surfaces of the inner wall here and the outer wall, that the temperatures are constant there. So we basically are not considering convection effects. And then there's this, what you just said, give me a second, that there's no heat transfer in Y and Z direction, so we only consider it along the X axis. And the fourth point that is quite important is that there's no heat generation within the wall. So there's only a transfer through the wall, but that there's no source of heat that heats up or cools down the wall. And for the parameters, you already mentioned quite a lot of them. So the width is important. Obviously, also the complete surface. The bigger the area of the wall, the more heat you can lose through it. The thermal conductivity and also the temperatures at the inside and the outside. Obviously, if the temperature gets bigger, there's a bigger heat transfer. And finally, the parameter that we want to calculate, and it's the flow into direction of x-axis. So, and yeah. Sorry? Why is it important? It shouldn't. So it's not important for the heat flux if you look at it per square meter, but it's important for the total heat flow. Because if you think that you have let's say you have a very small wall with a very small area, then obviously you can transfer less heat than if you have a very huge plane with a lot of space. Right, yeah. I just look at it in one dimension to simplify the calculation. Yeah. Otherwise, we would stay here for a few hours, and it's not in your and not in mine interest. Okay, so what is the heat loss through the wall? Once again, you need equations to describe your problem. And if you watch the videos, you will remember that there are two equations that we can use. Does anybody have an idea which equations I'm talking about? The heat diffusion equation, right? And the second one, it's also a law. No, convection we don't consider here. So the second one is about conduction, and the law describing the conduction is called Fourier's law. So that are the two equations that we require to solve this issue. So the top one, heat flux, equals to the minus lambda times the nabla of the temperature. So that's really Fourier's law, the basic idea on how the heat is transferred by conduction. And the heat diffusion equation allows you to describe it in a temporal, to describe the temperature with respect to the x, y, and z axis and the time. Okay, so then let's start with the heat diffusion equation. And now all the assumptions come into play that we just defined. So the first assumption, steady state. What is the consequence of it? Right, there's no temporal change. So basically this first one here is that the temporal change is always 0, and this means that if we that there's no time change for the temperature. So this is 0 right here. No heat generation inside the wall. What could that have for a consequence? So if you go back to the heat diffusion equation up here, you have the temporal changes, you have the changes in direction, and you have this additional source term. And this one has to be 0 as well if there's no heat generation or removal of heat inside the wall. And the second thing that we can also remove is the heat transfer in y and z direction, because we assume that it's only in one direction. And this leaves us with this equation here. So the left-hand side is 0. The right-hand side, the only remaining part is lambda times the partial derivative to the power of 2 of the temperature of with respect to x. And that's exactly what you can see here. And to solve this equation, to get a temperature profile, this should be really basic exercise for you. So you just integrate it twice. You get a linear relation. So for the first integration, you get one constant C1, and for the second integration, you get a second constant C2. So how can we now solve this equation? How can we get our constants? Right, the boundary conditions. And that was one of our assumptions as well, because we said the temperature at the inner side is equal to the temperature of the room. Temperature of the outer side is equal to the temperature of the environment. And this basically means that at the position x equals to 0, we have a temperature of T in. At the position of x equals to the width, W, we have a temperature of T out. And if you enter these two boundary conditions here, so let's start with 0. So if x is 0, T of 0 equals to C2, and T of 0 is T in. And you can do the same thing for the other boundary condition, and you end up with the calculation or the definition of the constant one. Right. Yeah. So it's defined here. It's the total width of the or the thickness of your wall, how thick it is.
So it's just like a slope of a linear function.
Sorry?
It's just like the constant C1 is just like a slope of a linear function.
Mm-hmm. Okay. Yeah, so that's, yeah, you basically just answered the next question. So if you look at now at the development through this wall, you can see that it's linear. So there's only a dependence of x, and that it's T in at the inside, T out at the outside. And so the heat conduction is, so the temperature profile along this wall is a linear function. Okay, so next we are not interested in the profile in the first place, but we're interested in the heat flow through the wall. And that's where we need Fourier's law once again. Because in this flux, so the conductive flux, we can use this conductive flux to calculate the total flow. Once again, we look at it in our coordinate. Sorry. I just saw an error. With coordinates. Okay. And what you so it's basically just math again. And then we have once again the assumption that there's no heat transfer in y and z direction, and that's why we can remove these two parameters. And now to get the total flow, this is also something I mentioned in the videos, you have to integrate, because we're not looking at the flow per square meter, but we are looking at the flow that we lose across the complete wall. And that's why we have to do the integration in direction of the height and also in direction of the length of the wall. So we include the complete surface of the wall. And that's written here. So you basically have the integration of your flux, conductive flux.
So, all right.
Yeah.
Conductive flux is just estimated by one dimension and heat transfer to carbon powder.
And no, so the heat transfer, so we looked at the temperature profile in X direction, and we assume that it's everywhere the same. So nevertheless which position we are, if we are at position y equals to L or y equals to half L, we always have the same temperature distribution if we move along the x-axis. And now we look at it, so you can think about it. So that's L, that's the height. And what we assume is that at every point here, I can choose whichever position I want to. We have the same heat flux. And that there's no difference if we move along the y-axis or if we move along the z-axis. That's our assumption. So in reality, if you look at complex examples, that's obviously not the case. Because maybe here at this position, there's air again, and then you have a little slightly different heat transfer in this direction, and this leads to a temperature profile which is different along the y and the z axis.
Okay. We made just a simplification because the gradient of the temperature is estimated in one direction.
Right. That's our simplification. So, I mean, when would it be valid? If you look at very huge areas where you have little change across our two dimensions. When wouldn't it be valid if you look at very small areas where you have a lot of change in the different directions? Okay, so this means we basically have to do math again and try to solve this equation. We know the temperature profile in x direction. It's a linear function of x. It doesn't depend on y, it doesn't depend on z. And this means we can move it in front of the integration signs and just do the integration from 0 to h, 0 to L, which is basically h and L. And what we now still have to do is to calculate the derivative of the temperature. We know it's linear, so if you derive it once, you end up with C1. And so that's the final result that we get for the heat flow through our wall. So you have minus lambda times the first constant times h10L. And So if you believe that it's right, or if you could follow my explanations, you can now understand what the importance of the different parameters is. So let's start very simply with lambda. So if you have a better or worse thermal conductivity, obviously the heat flux is going to increase or decrease. And same for the height and length. So as we do the integration across the complete area, it becomes clear that the bigger these two dimensions are, the bigger the heat flux, the heat flow will be through the wall. And for the thickness, or the width in our case, it's you can see that if you increase the width, the insulation gets better. So the heat flow through the wall will decrease. And this also makes somehow sense if you think about insulation of buildings. The bigger the wall, the harder it's for the temperature basically, or the heat to move through it, and the less the loss you will have in terms of insulation. And last but not least, obviously the temperature difference. So the higher the temperature difference, the stronger the flow. I think this is somehow also intuitive. Okay, are there any more questions to this first example? Okay. Then in the next step, I made it a little more complicated and added some layers and parameters. And the first thing so there are lots of similarities: steady state, no heat transfer in Y and Z direction, no heat generation inside the wall. I just added one difference. So I said that only the temperature of the surface, so the temperature at the outer surface equals to the temperature of the wall. And in the inner side, we have some kind of convection. And I also added a second layer. You will see later why I did this. So you will get an impression on how to simplify the calculation in the future, and that you don't have to do this complete procedure every time, once again and again. Yeah, so that's why we have this alpha as parameter, the heat transfer coefficient for the inner side. So at this moment, we don't really know, is it forced convection, is it natural convection, but it doesn't really matter, because you get these alpha values by doing experiments, and then the principle is the same, and it doesn't depend on your type of convection. Okay, so we do need the same equations, but we need one additional equation, which I also presented in the video. Does anybody have an idea what that could be? Sorry? Convection equation, right? And the convective heat flux is defined by this heat transfer coefficient times the delta T, so the temperature difference. Okay, so let's start again with the equation that we used just, I don't know, 5-10 minutes ago. So if you simplify it again, so it's steady state, you don't have any temporal changes. It's we assume that Y and Z is not important, and that there are no source terms. We end up with exactly the same equation describing our problem. So we end up with 0 equals to lambda and a double derivative of the temperature with respect to x. And if you solve this again, you will end up with the same equation. So there's no change compared to the example that we just did. So the only difference now is that it's a little harder to define our boundary conditions, because we don't really know what the temperature at this connecting layer is. We don't really know what the temperature at this position here is, because there's this convective heat transfer, and we still need to calculate it, but we still know the temperature at the outer side. And this basically means that we have to split our equations in 3 parts. So from -infinity, so from the left-hand side, up to the wall to 0, position x equals to 0, we have this temperature distribution, which is described by the convective heat transfer. So for the inner wall, 0 to W1, that's exactly what we had before. And for the outer wall, from W1 to W2, you have the same, but now you have to adjust. Well, we have the same, but we don't know what T2 really is. So you're doing the same, assuming that you know a temperature T1 here, T2 here, T1 here, and yeah, it becomes a little more clear in the next step. If we look at the profile, you will have the same that we had before. So there's a linear temperature profile in one layer, there's a linear temperature profile in the second layer, and there is somehow this convective temperature profile that I just discussed at the start of this lecture. Yeah. Okay, I continue with the complete slide. So what's important now, if you look at these equations, you can first see we know the convective heat flow by the definition that we just discussed. So it's minus alpha, the heat transfer coefficient, times the complete surface, times the temperature gradient from the inner air temperature to this temperature T1 at the inner side of the wall. Then we have exactly the same that we just derived in the first example, except that T1 is not equal to the inner temperature, and T2 is not equal to the outer temperature. But the form of the equation remains similar. And then we have the same thing for the outer layer. And now it's really important to understand what we know and what we don't know. And yeah, go for it.
I don't want to destroy it more, but isn't that the problem since it the gradient of the temperature? You would have step behavior. Once you change the water from that point, you want to W2. And the heat flux stepwise change.
Right, and that's a good point. That's exactly what is written here. So the heat flux doesn't really change. Because if you calculate the heat flux, if you look at Fourier's law, there is the temperature gradient and there is the thermal conductivity. And basically, if you have a bigger temperature gradient, the conductivity has to be lower. And that's how you can get, and yeah, what you just stated is that it's important that the heat flow or the heat flux remains constant along your x direction. Well, if you, I mean, that's what I try to describe here with this separation on the left-hand side. So these equations are only valid for their specific x dimensions. And for the boundary points where you would have this change, you have a defined temperature. And I think what you should pay attention is, let's say this is our wall. And what we don't do is that we take maybe this point and this point and build a gradient from here to here. This would be critical, but we only state that it's valid until this point, and that's why it's still true. Okay, and think again once again about Fourier's law. Because your initial idea is really good, that the heat flow or the heat flux shouldn't change. And if you think about Fourier's law, you will realize that if Q is constant, you have two parameters to play with to keep it constant. And one parameter is the gradient of the temperature, and one parameter is your thermal conductivity. Okay?
So you just define a separate
Mm-hmm. Yeah. Yeah. Yeah, that's it. And what is really important is that you really separate the different layers, because the equations are only valid for this particular material or this particular kind of convection. And that's why you always separate here. So it's valid from this position 0 to the position W1. And it's valid from the position W1 to this position W1 plus W2. Okay, so if you now look at the equations, once again, you have the heat convection at the inner side. You have the heat flow by conduction at the first and the second layer, which is written here. And you have, but you don't really know anything about the temperature T1 or the temperature T2 because they are unknown. You know, however, the boundary condition at this position, so this T out is known, and you also know the T in your convection equation. And if you now assume that the flow remains constant, so that there's no heating up or cooling down within your solids or gases or liquids, you can assume that this heat flow is constant for every of your layers. And this means that you have one constant at the left-hand side. So in total, you have three unknowns: the flow through your walls, the temperatures at the position T1 and T2. And you also have three equations, each equation for each layer. And yeah, if you, I guess you had a lot of math in your studies, and this sounds like a system that you are able to solve. Yeah, so, and that's what I did on this slide. I don't want to go into too much detail because it's only math, but you can move the left-hand side to the other side and add T in, then you end up with this equation. You can do the same thing for the temperature T2. You end up with this equation, and then you have to insert it into the other equations. That's a lot of calculus, but in principle, I guess that's just that are your basic tools that you are familiar with. And if you continue, you will end up with Q out, which equals to this equation here. Okay, so let's take one moment and do a step back to the first example. So if we just look at the first example, these two parameters here wouldn't be here, because there's no, the W2 would be 0, and there would be no, there would be no heat convection to the inner wall. And that's exactly the equation that we just had. So you have lambda times the gradient of the temperature divided by W1 times HL. And what we have now, by adding these two layers, you can see that it's very similar for the second layer. So the form is completely equal, except that you have other values for the width and other values for the thermal, for the heat conduction coefficient. And the third thing that we see here is the effect of the convection. So here's the heat transfer coefficient. And also what is important is the height and the length of the wall. And why I did this example a little bit more in detail and why I annoyed you with the calculation and so on is to come to this very interesting conclusion. So if you look closely at it, you can see that it's very similar to electronic circuit simulations. So instead of the voltage, you have a temperature difference across your elements, and instead of the so instead of the electric flux, you have a flow or a flux of heat. And the connecting element basically, or what you need to determine every time that you look at such an example, is the resistance, so the heat or thermal resistance. And this is this part on the right-hand side here. And the first thing that you should realize now is that these layers that we look here, these resistances that we have a look here, are in a certain order. And what is your guess? What kind of in what kind of order are the resistances? Yeah. Yeah, the direction is right. Yeah. Yeah. I guess you're on
the first row, and then on the
yeah. So basically you're on the right direction. So what you have is something that looks a little like this. So you have three resistances in the same direction. The first resistance is for the convective heat transfer. The second resistance is for the first layer of conduction, and the third resistance is for the second layer of conduction. And that's exactly what you can see here. So you have a resistance 1 plus a resistance 2 plus a resistance 3. And that's how you can simplify the heat transfer problems that we will discuss in the future and so on. It's also possible that they are in parallel. How would it look like then? Right, yeah, so if you look at it, so something like this is also possible, that you have two different layers. Let's say another one here. So then there are two resistances in parallel, and the next one is in serial again. And so the main advantage of this approach is that every time that you use that you find such a circuit analogy, you know what the resistance of your particular layer is. So for conduction, you always have these values, and for convection, you always have this part of the equation. And that's how you can really simplify very complex systems by using standard electronic circuit simulation tools. Okay, are there any questions regarding this aspect, or are you fine with it? Just as a note, in general, you can use the same laws that are valid for electronic circuit simulations. And a second point regarding this example, obviously let me just go back. This integration step is very important, because here in our case we have a very simple example. It's just a flat surface, but if we look at pipes, for instance, this will change completely, because pipes have a circular area. Let's say like this. So if we have a pipe that looks like this, and you want to measure the heat flux through the pipe, through the wall of the pipe, from temperature T1 to a temperature T2, the area of where the heat goes through will change, because the radius varies. This is R, So at the inner side, you have a very small area. And the further you go outside, the bigger the area gets. Or cylindrical, depending on what you do. If you look at the classical pipes, you would work with cylindrical coordinates. And this would automatically lead to a different behavior also regarding the temperature profile. It wouldn't be linear, but it would be somehow quadratic. Okay, so that's it for the for heat transfer. If you could follow here, the diffusion part will be really simple for you, because we're basically there are lots of similarities between both topics, and both topics have also lots of similarities with this electronic circuit principle. So let's start shortly with a discussion of the different matters. So in case of diffusion, we always look at a solute and a solvent. So the solvent is basically the matter that is where you have more of it, and the solute is introduced into this matter. Like if you look at iron and you have hydrogen which moves along the iron or through the iron, then you would have the solvent iron and the solute hydrogen. If we now look at the parameters, you see that the diffusion coefficient is bigger for gases and gets lower and lower the more you, the closer you get to solids. And same principle as before. So look at the micro scale, think about what's going on the micro level, and it's basically the same point that we made half an hour ago. So the closer the molecules are packed together, the harder it is for other molecules to move through them or to get through them. And in case of diffusion, you can see that this diffusion coefficient can really vary up to a very high degree, up to the power of 8. Okay, and as an example, we will also look into hydrogen loss through a wall. So also the question is already in a very similar type as the heat flow question I just asked you. Why is that relevant? Basically, there are macro examples, there are micro examples. Let's start with the macro. So if you have a very huge gas tank, you don't want to lose all the hydrogen through the walls, and that's why you have to pay attention on how you design it and how you make sure that all of the hydrogen remains within your tank. And for microfluidics, diffusion is really interesting because we are shrinking down all the dimensions, and that's why you always are very close, or different liquids are very close to each other. And you can use this effect to efficiently mix liquids. It's presented in this picture here. So you have a blue liquid and a red liquid, and by implementing this cascade structure, you are able to do a concentration gradient. So on the left-hand side, you have the blue liquid, on the right-hand side, the red one, and in between you have mixtures of both liquids. I don't want to go into detail into this principle. I think Niklas will talk a lot about it in later lectures when he's going to introduce this scaling effects and when he's going to talk about pump-driven microfluidics. But keep in mind that diffusion is especially interesting in microfluidics and is not Okay, so let's start again with our modeling approach. So once again, you have a flow through a wall. You have similar parameters, the width of the wall, the height of the wall, the length of the wall. Instead of the temperatures, we now have the concentrations. So there is a concentration of our reagent in the inner side and in the outer side. And if we now think about the assumptions, I mean, you should come to a quick conclusion. So what do you think could be a valid assumption for this case? Yeah. Yeah, right. Yeah, so it's exactly, yeah, it's definitely, yeah, that's it. So steady state, we assume that the concentrations are constant within in the inside and the outside, so that there are no variations or things like convective transport that disturb our concentrations. We assume that there's no diffusive transport in Y and Z direction, and that there's no species generation inside the wall. So species generation, this can occur typically by chemical or biological reactions. So we assume that there's nothing like this in our case. Similar parameters. So the only thing that changes basically is that we are not talking about the thermal conductivity, but the diffusion coefficient, and that we are not talking about the temperatures, but the concentrations instead. And this is only possible because the equations are very similar. And what we need here is Fick's first law and Fick's second law. And once again, think about the temperature equations. You will see that they are very, very similar, except that the naming or the names of the equation changes. And this should, I really try to repeat it as often as possible, because this will help you in the future. If you have to solve one of those problems, you will always remember, okay, I did something like this with temperatures already, or I did something like this with concentrations, and then you can always use the same tools for different problems. Okay, then let's start again. What can we remove from Fick's second law? Go to the assumptions, steady state, no species generation inside the wall, and constant along the Y and Z axis. So what can we remove? Yeah, concentration change, the source terms, and obviously in temperature concentration changes in temporal or in direction of Y and Z. Okay, we come to the same equation like we had before, except that it's not temperature but concentration. So it's you have to integrate your Fick's second law twice, and you end up with a linear concentration distribution. And you have the same boundary conditions that we had before. So at the position x equals to 0, the concentration is C in. At the position x equals to W, the concentration is C out. And that's how you calculate your constants. So big C2 and here's C1. And you see that the concentration distribution is similar. So keep in mind what I just mentioned with the tube. For this case of a flat wall and or an infinite surface, the concentration is linear. If you have other types of geometries, it doesn't have to be necessarily linear. So in case of the tube, it changes into another type of distribution. You then use again Fick's first law. So Fick's first law is really the same thing like Fourier's law, and the Fick's second law is basically the heat diffusion equation. We once again state that there's no diffusion in Y and Z direction. You can get rid of dy and dz. And you then do the integration along the surface where C only depends on X. And yeah, that's so you end up with the same things. Do the integration, you do you build the derivative of the concentration, you end up with this equation. And once again, you can see that the influence parameters are quite similar. So if you have a bigger surface, meaning a higher age, a higher height, a higher length of your wall, you will have a bigger loss. And this makes somehow sense because the molecules can move through your wall at different positions. And the higher the surface, the more places they have to move through your wall. The thickness is important. The thicker, the harder it is for the molecules to move through your wall. And obviously also the diffusivity is important because if you have you can think about it like a grid. If you have big holes, the molecules can just move through. But if the grid is very tiny, it's almost impossible for the molecules to move through it. And finally, the concentration difference is important. So if you have lots of molecules inside and no molecules outside, the driving force or the heat, the concentration flux obviously is also bigger. So in this case, I prepared some data so that you get an impression of how important this heat flow is. And I did a calculation for a wall of 1 square meter, a thickness of 1 centimeter, so it's not a lot. And I did a calculation for hydrogen through iron. So it should be the same value as in the table that I just presented you. And what you end up with is that within a day, so for 24 hours, you lose about 3.6 gram. So that doesn't sound a lot. And this is where I want to mention that you always have to come back from macro problems to micro problems. And that's why diffusion gets more and more important the smaller your dimensions are. So if you have a huge hydrogen tank, this probably is negligible. But if you have only very little of substance and you lose that, you can quickly lose that by diffusion. Okay, are there questions for the diffusion exercise? So yeah, keep in mind, diffusion, heat transfer, those two effects are very similar. You can use the same tools, you can use the resistance calculation and so on. And if you have understood one of them, you also have understood the other one. Okay, thank you for your attention. And I guess I hand over the word to Judith.